everybody. Welcome back. Okay, so again, I got a question about 5, and 5A says to find an unbiased estimator based on the MLE. So this is a Pareto distribution. And the MLE problem is pretty standard. So you would find for part A, the MLE, which would be gamma hat, and that doesn't look like a gamma. And then you would look at the expectation, and you're going to get something, right? This is not, I don't know what it is. This is made up. But then you would have, if that was the case, n over n minus 1 times your estimator would be the unbiased estimator that was made from the MLE by adjusting it. That's what it meant to say find an unbiased estimator based on the MLE. Part B, we haven't done this. We're going to do this today, but the efficiency of an estimator is the Premier-Rao lower bound for the thing you're estimating divided by the variance of, I'm sorry, this is a gamma, so let me put gammas in here, of gamma, and then the variance of gamma hat. So this is kind of a long problem because you have to do the Premier-Rao lower bound, and you also have to take whatever your estimator, your MLE was in part A, and work out the variance and just form that ratio. And I do want to take time to talk about this on its own, but the Premier-Rao lower bound, as long as you have an unbiased estimator, is supposed to be smaller than the variance. So this number is less than or equal to 1 for unbiased estimators. And we say that an estimator is efficient if that thing is equal to 1. And in part 5C, you're looking for efficiency in the limit. So for part B, you want to compute this, and we're going to have lots more practice with Premier-Rao lower bounds today. In fact, yeah, a lot more. I was going to say, in fact, we haven't done any, but we did do the Bernoulli. And in part C, you just want to show that the limit as n goes to infinity of this thing I just circled is going to 1. We were talking about computational simplifications for the Premier-Rao lower bound. And we had 3, and we proved 1, and we were in the middle of the second proof for the CRLB. So number 1 was the expected value of the derivative with respect to theta of the log of f of the vector x, capital, so random, and theta is 0. And the thing inside that expectation is known as a score function for non-obvious reasons, but it is giving a score to a certain model versus another model when you're trying to choose a model to fit some data. And the second thing was that the expected value of the derivative with respect to theta of the log of the joint PDF, all of that squared inside the expectation. Now that's the Fisher information. That's the thing we need to find for the denominator for the Premier-Rao lower bound. And this is the same thing as the negative expected value second derivative without the squared. And second derivatives often make the expectation easier, but sometimes they don't. So you use the one that works for you, and we're going to do examples today. Now, the proof of this, we were in the middle of. So from 1, we have that the expected value of the derivative with respect to theta of the log of the joint PDF and theta is 0. And if we write that out with an integral, this is, let me move over here. This is the integral of the derivative with respect to theta of the log of f of little x and theta. And we're trying to find the expected value of that sort of thing. So we need to multiply by the joint PDF and integrate over all of the x's. And again, the vector over the x is telling you this is an n-dimensional integral. The integral is actually n of them going over dx1, dx2 out through dxn. So we already established this fact from property 1. And now I'm going to take the derivative with respect to theta on both sides of this. On the right side, we're still going to have 0. On the left side, I'm going to pass the derivative through the integral, which was one of the regularity conditions we were assuming. And then I'm going to take the derivative of this product of things using a product rule. So I have the integral of the first thing times the derivative of the second. So here's the first thing. And the derivative of the second is just d theta of the joint PDF. And then I have plus the second thing times the derivative of the first. So after I would write that down, I would spread the integral out. I would run it across the sum. I'm just going to do that right now so I don't have to write the line again. This is going to be plus the second thing times the derivative of the first. So when I take the derivative of this derivative, that's where we get a second derivative. And then the second guy is just sitting there. And this whole thing is supposed to equal 0. So you can see down here, the second integral, it is the integral of a certain function of x against the joint PDF. So this is actually the expected value of that function with capital X's plugged in. And if we move that to the right-hand side of this equation, we'll have the negative of that. So hopefully this is the original Fisher information, because that's what I'm trying to show. I'm trying to show that the original Fisher information is the negative of the expected value of this second derivative. And we can get that that first term here is the original Fisher information. This is really hard for note taking. I'm being sloppy, but I'm kind of rushing because I want to get to some examples. Right now, the thing I circled in yellow is not an expectation because it's not an integral against the joint PDF. It's against the derivative of the joint PDF. But if we rewrite this as the derivative with respect to theta, so this first log term is just going to sit there. And then I'm going to write the derivative of f as the derivative of the log of f times f. Because think about it, the derivative of that log is the derivative of f over f. So the f in the denominator will cancel with this extra f that I put in there. And really this product is just the derivative of f. Now I've got two of the same expressions, the derivative of the log. So this is one of those derivatives squared times the joint PDF. And that is an expectation. That is going to be the expected value of whatever is here, which is this thing squared. I don't know if it was worth, I probably should have just slowed down and done it neater. But the circled thing at the very top of the screen is equal to this integral. And we've got a PDF here, and the stuff in front gives you one of those squared. So what we have shown is that the expected value of the derivative with respect to theta of the log of f of capital X and theta all squared plus the expected value of the second derivative, we've shown that this is 0. And that's what we wanted to show, because really we were trying to show that this is the negative of the other expectation. So move that one to the other side. That makes sense? At least maybe the process, because I know that was kind of messy. So the process is to start with number 1, to write out what it is as an integral, to take the derivative on both sides, to pull the derivative past the integral, and to do a product rule here, and then some manipulating to get the expectations back. Fun stuff. Okay, the third thing in the list is going to be really good for us because everything for us is IID. And so this says that if x1 through xn are IID, because the Chimera lower bound was defined using a joint PDF, and that joint PDF actually doesn't have to come from multiplying the individual single PDF over and over again. They could have different PDFs, so different distributions. They might not even be independent, but you can somehow write down a joint PDF to describe the behavior of the whole vector. But in the case they're IID, the Fisher information, that was the notation for this expectation up here, is n times the so-called one-dimensional Fisher information. So the Fisher information, I don't think I recapped this here, is the expected value of the derivative with respect to theta of the log of f of the vector and theta, and all of that gets squared. And then that n is coming from that subscript n is coming from the fact that it's a vector of length n. And if you just look at a vector of length 1, since these are IID, I can use any one of the x's. That is the expected value of the derivative with respect to theta of the log of f of just x1 or x7, all of that squared. And this is really nice because we did one Bernoulli example and we wrote out our PDF, then our joint PDF. We took the log, took the derivative, squared it, put it in an expectation. We ended up seeing a sum of Bernoullis, and we used the fact that that was binomial. But if you use this computational simplification, you can just compute a one-dimensional Fisher information, so you can work directly with the Bernoulli, and you won't get that sum of the x's, which can be significantly harder for different kinds of problems. I do want to take the time to prove this, even though I'm tempted to just jump to examples because there's a couple of things to learn out of this proof. So um, let's look at the n-dimensional Fisher information. It is defined to be, oh, and by the way, sorry about this. If I go back up to the line above, we can use our second derivative definition when we have a vector of length 1. So this is also the negative of the expected value of the second derivative of the log of f of x1 and theta. But going back to my proof, so it's the expected value of, I'm going to use the squared version. Note that this thing inside the joint PDF, actually, let me make this bracket even smaller. This joint PDF, because they're IID, comes from a product from 1 to n of f of each xi and theta. Because they're IID. And when you take the log of that, it turns into a sum of logs. And when you take the derivative of that, the derivative can pass by the sum. So continuing from here, this is the expected value of the sum as I goes from 1 to n of the derivative with respect to theta of the log of f of xi and theta. So again, what I did there is write the joint PDF as a product of individual ones. I took the log, and the log of the product is the sum of the logs. Then I took the derivative and I pulled that inside the sum. To deal with this, I'm going to multiply 2 copies. So I'm going to rewrite this. I'm going to write out 2 copies, and I'm going to give them different indices so we don't confuse anything with the individual terms. So here's one, and now I'm going to write one with a j, d theta, log f, fxj, and theta. I can pull the j stuff kind of inside the sum here of the I sum. And so really what we have is a double sum. I goes from 1 to n, j goes from 1 to n, one of them, and then the other one. And I can pull those sums out of the expectation, and I have nothing to worry about in terms of is that valid, even though you don't have to justify in this class because finite sums will always be valid to pull them out of an expectation. It's just that if they're infinite, does the sum converge in both cases when it's inside and outside the expectation? But right now I've got the derivative with respect to theta of the log of f of xi and theta, and the same thing with an xj. And we need to sum these up. So we need to determine these expectations. And you can see that there's like a sum over I and a sum over j. There's a total of n squared terms. And for me, it helps to like organize them in terms of a matrix, like say I is 1, 2, up through n, and then j is 1, 2, out through n. And think of the ijth entry of this matrix as this expectation. When we're on the diagonal of this matrix, I equals j, and we have a certain expectation. And when we're off the diagonal, I is not j, and we're going to have a certain expectation there. So we have n, these are along the diagonal, terms where I equals j. And in that case, we're looking at the expected value. So our expectation with the I and the j is just the expected value of one of them, let's say the I squared. So the line above is just the individual thing. One of them has an I and one of them has a j. And this is, what am I trying to show? Oh yeah, this is the one, there's only one thing in here. This is not a vector of length n. This is the one-dimensional Fisher information. And there's n of those. So looking back at my matrix, terms like this for the ijth entry, looking off the diagonal, I have a total of n squared terms, and I'm going to take away the n terms on the diagonal. And for those terms, I is not j. So we also have n squared minus n terms where I is not equal to j. And in that case, maybe I should write it now because I'm off screen, the log f xi and theta, and the other one has the xj in it. In this case, they're independent terms because the x's are independent, and we've got a function of xi and a function of xj, and xi is not equal to xj. So by independence, we get the expected value of the derivative with respect to theta of the log of f of xi and theta times the same expectation, but with an xj in it. And each of those is the expectation of the score function from property 1. These are both 0. This is by property 1 in this list, so 0. So to finish this off, I started with the n-dimensional Fisher information. I wrote it as a double sum of things. We just realized that a whole lot of those things are 0. And if you arrange those terms in a matrix, everything off the diagonal is 0, and everything on the diagonal is equal to the one-dimensional Fisher information. So we now have that in of theta is n times the one-dimensional Fisher information plus, and you obviously don't need this, but n squared minus n times 0. So we get n times the one-dimensional Fisher information, which is what we were trying to show. You can be asked in the future, and on maybe you'll see it on exam review problems, to be able to deal with some of these expectations, like pulling the trick of like this big yellow circle towards the top. You might be asked, and you'll get practice, to write that as an expectation. And the goal is to make this second thing really into a PDF, so to play that log trick. But that sounds scary now, but we're going to have lots of experience. But my point is that this is not like our usual, I have to do this technically, but then you only worry about the numerical examples. You may be asked to do some of these small calculations like inequality from one line to the next line, but not the whole thing. And again, you'll get practice. But let's do an example. Okay, so for this example, I'm going to take x1 through xn, a random sample, same thing as IID, from the gamma distribution with parameters 5 and beta. Or I could have said alpha and beta, where alpha is fixed and known. And I want to find the Cramér-Rao lower bound for the variance of all possible unbiased estimators of beta. And that's usually written in shorthand as the Crumier lower bound for beta, but it's not bounding beta. So the variance of all possible unbiased estimators of beta. Right, so the PDF. This is just the one-dimensional PDF. This is 1 over gamma of 5, beta to the 5, x to the 5 minus 1, or 4, e to the minus beta x, and an indicator, which we're just going to drop anyway. I'm going to drop it because, well, it's weird to take the log of it. But after that, if you took the derivative, it would disappear anyway because it's a derivative with respect to beta. And as you know, the only time it really becomes important is if the parameter is in the indicator, but you're not allowed to use the Crumier lower bound in that case because it doesn't satisfy the regularity conditions we needed for the proof. So I'm just gonna like ignore rather than dragging it through the problem. It's pretty messy. And again, the cases where it's important, where the parameter is in the indicator, you should not be doing a Crumier lower bound. And I'm not going to try to trick you by asking you to do a Crumier lower bound in that case. Anyway, our next step was usually to write the joint PDF, but I'm going to try to use this one-dimensional Fisher information. So I'm going to take the log of this, and I've got a bunch of things like a bunch of products, and those will turn into sums, and I'll bring exponents down and stuff. This is the log of 1 over the gamma function of 5, which is a constant, and then plus 5 times the log of beta plus 4 times the log of x minus beta x. Next up, I'm going to take the derivative with respect to beta. Again, trying to build up that Fisher information. The first thing with the gamma function disappears. There's no beta there. So I'm going to write a 0, and then we get 5 over beta by taking the derivative of the log of beta. And then the 4 log of x term disappears because there's no beta there. And then we get a minus x. So 5 over beta minus x. For this problem, I think the second derivative is easier, but I want to show you both because neither is going to take very much time. The one-dimensional Fisher information as a function of the parameter beta, one way to define this is the expected value of the derivative with respect to beta of the log. Out of habit, I was putting vectors here when I was only working with one. So neither of those vectors should be there. I won't just erase them. I'll just, because it'd be hard to figure out what I changed and cross them out. Sorry about that. Going back to my one-dimensional Fisher information, I can take the derivative of the log of the PDF, not the joint PDF, but the single PDF, and square it. So we worked out that thing inside the parentheses. This is the expected value of 5 over beta minus x1 squared, which, because it's squared, I can write this the other way. This is x1 minus 5 over beta squared, and this is the expected value of x1, because that's going to be alpha over beta because x1 had a gamma distribution, but alpha was given to be 5 here. So this whole thing is the variance of x1. And if you look up the variance for the gamma, that is alpha over beta squared. So we get 5 over beta squared. I'm not finished with the problem. I need to multiply by n to get the n-dimensional Fisher information, and then finally make the whole Crumier-Rao lower bound expression, which had a derivative of tau squared in the numerator. But before doing that, I just want to go to an alternative way to do this with the second derivative. So we showed that this is also the negative of the expected value of the second derivative with respect to beta. Man, I'm doing this all over the place. Another kind of error, I guess I can claim it's a generic parameter, but here I put a theta when that's really a beta. Sorry about that. The log of f of x1 and beta. So we had the derivative with respect to beta of the log of f of x1 and beta. That was equal to 5 over beta minus x1. And so if we go for the second derivative, then that x part is going to disappear. This is the derivative with respect to beta of 5 over beta minus x1. That is a beta to the -1, so I get negative beta to the -2. I get -5 over beta squared. And so going back to the thing that's just peeking off the top of the screen now, the one-dimensional Fisher information is the negative of the expected value of that second derivative. So it's the negative of the expected value of -5 over beta squared, but there's no x's there. That's just a constant. So we get the negative of -5 over beta squared and just 5 over beta squared, which is what we got the other way, with our other computation for the one-dimensional Fisher information. So this one was quite nice because even though it wasn't hard to compute the variance, to look it up, there was actually no expectation to be done here. So the second derivative made it significantly easier. Well, I don't know, significantly is in the eye of the beholder, but I think it made it easier, but sometimes second derivatives make things worse. So going back to the Cramér-Rao lower bound, I want the CRLB, and I'm going to put a sub beta that is representing a Cramér-Rao lower bound for the variance of all unbiased estimators of beta. The formula is tau prime of beta squared over the n-dimensional Fisher information. And here, tau of beta is beta itself. We're not trying to find the Cramér-Rao lower bound for the variance of all unbiased estimators of e to the beta. We're looking at beta itself. And the n-dimensional Fisher information, because these are IID, this is n times the one-dimensional Fisher information that we just found. So this is 5n over beta squared. And the derivative of this tau with respect to beta is 1. So we are done. The Cramér-Rao lower bound for beta is 1 squared over 5n over beta squared, or beta squared over 5n. I know that looks like a lot, but you'll see once you do, it's just the same thing over and over again. It's very mechanical. So by the time we get to the exam, I think this will just be, you won't even have to think about how to do a Cramér-Rao lower bound by that point. We were talking about estimation. We talked about method of moments estimators and then maximum likelihood estimators. And then for some reason, I took this diversion into the Cramér-Rao lower bound. And this is why. I would like to give you a list of nice properties of MLEs, most MLEs. And this is going to hold under certain regularity conditions. There are going to be the same ones that we needed for the Cramér-Rao lower bound, and a couple of others. And these are just things that make things nice. Like, does the second derivative even exist? Can you take the log of the derivative, or is that somehow undefined because the derivative gave you negatives or something like that? So I'm not going to write the regularity conditions. I'm just going to say again that these properties may fail when the parameters are in the indicator, but they also may hold, and they do hold in some cases. So those regularity conditions would really be sufficient and not necessary conditions to get these properties. So again, all of our nice known name distributions without the parameter in the indicator satisfies the properties I'm about to write. And when the parameters is in the indicator, they may also satisfy some of these, but we're going to do a couple of proofs, and our proof is going to assume we can do things like this with the derivatives. So property 1 is that, actually, sorry, before I write the property, I'm going to let theta hat be an MLE for theta in some problem. So there is an underlying x1 through xn with the joint PDF that depends on theta. And I may write theta hat n as theta n to really stress the dependence on n. So not, just a change of notation. Okay. So under the regularity conditions, under nice conditions, number one, the MLE exists and is unique. That actually holds for everything on our table that does have the parameter in the indicator as well. So there is a maximum, and the likelihoods, while they could be bimodal, this still has only one maximum, and it occurs right here. So under some regularity conditions, we're not going to see something bimodal with the exact same maximum. And I don't think that one's so interesting to prove because you just have to go through it and talk about when a maximum for a function might exist. There's all these cases if it's bounded and you're on a compact interval, or there's just lots of little. This isn't really MLE specific. It's more about when a maximum exists and is unique for a function in general. Okay, so number two is that theta n hat is a consistent estimator of theta, and that means it converges in probability. So theta n hat goes in probability to theta. This is something we've already proven in the case of the uniform zero theta distribution. So that does not satisfy the regularity conditions, but this would be an example of this can still hold. It's just that if you want a whole list of properties totally proven, then you do need to restrict yourself to PDF or the parameters, not the indicator. But for the uniform zero theta, the MLE was the maximum. And we know that that's a biased estimator, but we were able to show using that theorem that it converged in probability and was a consistent estimator for theta. So I shouldn't write example because that's not an example of what's going on in this list. That's just me saying again that these properties can hold even when the parameters in the indicator, they're just not guaranteed to hold. Okay, next up, all MLEs are asymptotically unbiased for theta. And that means that the limit as n goes to infinity of the expected value, we've seen that many of them are biased, so that expectation is not necessarily theta, but in the limit it will be. This next one, the terminology isn't going to make sense because I forgot to define something before this list, so I'll define it afterwards. But we say that theta n hat is asymptotically efficient. I forgot to define efficient outside of what we talked about at the very beginning. And efficiency is talking about how optimal the variance is getting. This kind of means, but this is wrong. This kind of means that the limit as n goes to infinity of the variance of theta n hat, that variance is getting down to the Cramér-Rao lower bound. So you kind of want to think like this, but this would be wrong. And the reason it's wrong is because the Cramér-Rao lower bound also depends on n. But this is the idea, the variance is getting close to the Cramér-Rao lower bound. And how we say this, because you don't want an n on the right-hand side of that limit, we say the limit as n goes to infinity of the Cramér-Rao lower bound for theta divided by the variance for theta n hat. This goes to 1. I meant to define efficiency before we went in, but this thing that we're taking a limit of, this is the efficiency of the estimator theta hat. So in problem 5b, you want to compute that thing I've just circled, and in problem 5c, you want to look at this limit. Because MLEs are, they're not always unbiased. They're definitely not always unbiased. you can actually get something with an efficiency greater than 1, meaning the variance can get below the Crimea lower bound because the variance is always greater than or equal to the Crimea lower bound, making this thing less than or equal to 1 if you're restricting yourself to unbiased estimators. But the MLEs are sometimes biased, so you would get what is known as a super efficient estimator, where the variance is actually smaller than the Crimea lower bound, which shouldn't be applying because it's a biased estimator. But still in the limit, they come together. And the final thing is, under some nice conditions, they are all asymptotically normal. The MLE is asymptotically normal with the correct mean, the theta you're trying to estimate, and the variance equal to the Crimea lower bound, which is sort of the same thing we were saying in 4, but in 4 we weren't saying the normality part. So a bunch of these things in the list there's some overlap. Like if we can show this last one, we've got that it's asymptotically unbiased because this is the asymptotic mean. And we've got that it's because we also get asymptotic efficiency because of how we define asymptotically normal with a ratio and stuff. So i.e. theta n hat minus theta over the square root of the Crimea-Rao lower bound for theta is converging in distribution to a normal 0-1 distribution. And you can use that doing statistics. Like if you need to make a confidence interval or do a hypothesis test, construct a test for something, and you don't have any good common sense estimators to use because the PDF is just really complicated and it's not clear how to interpret the parameter, you could find the MLE, the maximum likelihood estimator, and then use the fact that the MLE is getting roughly normal for large samples. So you can use normal critical values and cutoffs in confidence intervals and hypothesis testing for approximate confidence intervals and hypothesis tests. That's going to open up a whole lot of things to us because life is not so nice as MathStat. We can't always compute the distributions via moment generating functions and stuff like that. I am just going to take a second to look at the homework and make sure. The next thing I wanted to do was to prove at least one of these things in the list, but I'm going to instead give an inequality that I think everyone should know, but it wasn't really in this class, but the grad students need it for problem 7, I think. Oh, no. Yes. Sorry, I thought it was a different problem. So here is an inequality for the undergrads. This is sort of for both of you. It should be out of the blue, but useful for problem 7. And undergrads, don't tune out because this may be useful for you in the future. Useful for problem 7 on homework 8. This is known as Jensen's inequality. And it's about taking expectations through functions. So let x be a random variable and let g be a convex function. I'll remind you of what that is. If you're used to saying concave up and concave down, this is concave up, but I doubt you'll find Jensen's inequality written that way. So this is some function that looks like this. Okay, Jensen's inequality says that the expected value of g of capital X is, I can never remember which way this goes until I prove it. So this is going to be less than or equal to or greater than or equal to g of the expected value of X. And we're going to figure out which one now, which will end up proving it if I had stated it correctly. Okay, I'm going to let mu be the expected value of X. And then I'm going to consider the point mu on this graph. So I'm going to look at the graph of G. And I'm going to look at the point mu. And where we hit G, this is G of mu, which is the right-hand side over here. That's G of mu if I change the notation to mu. And if I look at a tangent line to the curve at that point, by convexity, the curve is always going to be above this tangent line there. So this is a tangent at x equals mu. And we can write this line, like equation of the line, as some slope. I'm going to call m with, oh, that's my slope m, a lot of bumps. X minus mu plus g of mu, like y equals some slope going through the point mu comma g of mu. The point slope form of the line. So g is convex, and that means that g of x is always greater than or equal to, let me move this over where it will fit, that line. I'm going to put capital letters in here. And I'm going to take expectations across. And I guess I've never proven that if a random variable x is less than a random variable y, that the expectations will be ordered in that way. But what does it mean for a random variable to be less than another random variable? It means that it will be smaller with probability 1. I shouldn't have even brought that up. Just pretend you can take expectations across this, because you can. This is greater than or equal to the expected value of this side. And when I run that through, I will bypass drawing a beta, bypass the m. I will have the expected value of x minus mu plus g of mu, because that's a constant and non-random. So the expected value of g of mu is g of mu. And the expected value of x is mu. So I get 0 plus g of mu. And that is g of the expected value of x. So we have shown, here is Jensen's inequality, since I never gave you the direction. If g is convex, which means it's like concave up, the expected value of g of x is greater than or equal to g of the expected value of x. So that holds for any functions that look like this. And if you have something that is concave down, or concave, if you're using the language of convex and concave, so g concave, that's something that, concave down, then this implies that the negative of g is convex. And you can use Jensen's inequality on the negative of g. So we have the expected value of negative g of x greater than or equal to negative g of the expected value of x. And if you multiply both sides by -1, the inequality flips. And you get the expected value of g of x less than or equal to g of the expected value of x. It's never stated that way, but certainly equivalent. But this is Jensen's inequality, and I think you can use it in problem 7 using the fact that log looks like this. Log is a concave or concave down function. So grad students doing problem 7, you will probably be pulling a log past an expectation at some point. But not in part A. Part A is so much easier than it looks like it is. It's the weak law of large numbers. I'm out of time. And we could talk about it now because it's my office hour, but thank you and bye.